Hello, I'm Mr. McBrien. This is SCH3U, Moles and Entities from Mass. The Ontario curriculum specifies that students will describe the relationship between Avogadro's number, the mole concept, and the molar mass of any given substance. That's what we're going to cover today. So, we're going to look at moles from mass again, calculating the number of moles in a sample, and apply that concept to a fairly real-world example, starting material for a reaction. We'll attack the worksheets for a bit, and then we'll talk about particles from mass, something we haven't really done before. In the classroom, we're going to do selected problems. For our purposes here, I'll run through a quick question on paper. Okay, so mass from number of moles. The mass is equal to the number of moles times the molar mass. We've covered this previously. Now, we can of course rearrange this. If we divide both sides by the molar mass, we get N equals the mass over the molar mass. The number of moles is equal to the mass divided by the molar mass. Okay, so this is the equation we're going to use for the first part of today. So a quick example. So let's say we've got a 4.02 gram silver ring, and we want to know how many moles are in it. From our handy periodic table, the molar mass for silver is 107.9 grams per mole. Use our equation, and we can get 4.02 grams divided by 107.9 grams per mole gives us 0.0373 moles of silver. Pretty straightforward. So, what about sodium hydroxide? So, in this 1 pound container of household lye, how many moles of sodium hydroxide? Well, first off, we have to use our newfound skill of calculating the molar mass for a compound. So sodium 23 grams, oxygen 16 grams, hydrogen 1 gram per mole, totals up to 40.0 grams per mole for sodium hydroxide. And once we have this, fairly trivial, N equals M over M. 454 grams divided by 40 grams per mole gives us 11.4 moles of sodium hydroxide in our 1 pound canister. Okay, but those are all things that we are not likely to apply on a day-to-day basis. So why don't we go back to our synthesis of Celebrex to talk about applying this concept. So given a target mass for a synthesis, how much of each starting material should we use? And we're going to do this problem in 2 steps because I think it's a little easier to follow that way. So let's go back to our synthesis of Celebrex equation, take our finished product, and assume that our chemical engineers at Pfizer in Singapore need to make 100,000 200 milligram tablets. So that's 20,000 grams of Celebrex. They need this for the batch. So we can quickly total up the atoms in our structure to get the molar mass. I'm not going to go through that. You could do that manually, but the mass is 381.372 grams per mole. So our first step is to say how many moles of Celebrex do we need. And this is exactly the calculation that the engineers at Pfizer would do. So they know the molar mass of Celebrex. They know the equation for number of moles from mass, and they know the number of grams they need. So pretty quickly we can find that we need 52.44 moles, and Of course, they're going to allow for some wastage. They're going to have a good idea of the efficiency. Let's, for our purposes, assume that the efficiency is going to be about 100%. So they're going to get out what they put in, roughly. But they're going to make a little extra. So why don't we make 53 moles to allow for wastage? Well, our two products are here. It's a 1-to-1 ratio. So for every mole of Celebrex, we're going to need a mole of this stuff and a mole of this stuff. So for 53 moles, we're going to need 53 moles of both of these starting materials. So how much of the starting materials do we need? Well, again, they can't weigh this out on a balance, so they need to convert to grams. So step 2 of our calculation is to find the mass of the two starting materials if we have 53 moles. So we have to get the molar mass of the two starting materials. Again, we just total up each one of the atoms. So the first one's formula is this, and we get 230.18 grams per mole. The second one's formula is this, 187.22 grams per mole. Okay, so how many grams is that? We have to do a two-part calculation. There's really no way to combine these two. And it's just the same calculation over again. Mass equals N times M. 53 moles times 187 grams per mole gives us 9,900 grams. On the other side, 53 moles times 230 grams per mole gives us 12,190 grams. So, in order to make their 100,000 tablets, they're going to need to add 9.9 kilograms of one starting material and 12.2 kilograms of the other starting material. Okay, so let's practice doing those kinds of calculations. Please pull out the worksheet and do questions 1A, 2A, 3, and 4 on each sheet. And for those at home, the answer sheets are up on the bulletin board. For those in class, they're on the bulletin board. For you at home, you'll need to download the solutions from the website. Okay, welcome back. Hopefully you've worked your way through the worksheet. Let's talk about getting number of entities from mass. So we already know how to get the number of particles from the number of moles, and we know how to get the number of moles from the mass. So there's no reason we can't get the number of particles directly from the mass. We simply need to manipulate the equations. So if the number of moles equals the mass over the molar mass, and the number of particles equals the number of moles times Avogadro's number, we can substitute in m over m for the number of moles and get number of particles equals the mass divided by the molar mass times Avogadro's number. So let's try it out. Let's say we wanted to know how many acetaminophen molecules were in a 200 milligram tablet. We can simply calculate the molar mass for acetaminophen, adding up again the coefficients for each one of the elements to get 151 grams per mole. Substitute into our new combined equation, giving 0.200 grams divided by 151 grams per mole times Avogadro's number. Gives us 7.97 times 10 to the 20 molecules. And we can debate again about significant figures here, but since we know it's a 200 milligram tablet, we know that drug companies are going to be pretty careful to try to keep that accurate, so we can take that as 3 significant figures in our tablet. Okay, another example. In the classroom, I'm going to take this up on the board. However, I'll try to the document camera here to do this one in the video. So my 24 karat, and for those of you who are scholars, you'll know that 24 karat means pure gold. My pure gold ring has 3.01 times 10 to the 22 atoms in it. And the question is, what does it weigh? So let's do that calculation to find out how many grams of gold are in the ring. We could do it stepwise, but for fun, let's do this in one step this time. So, what we need to do is find the mass. And we've seen that the mass equals Nm, but N is also equal to the number of atoms divided by Avogadro's number. So the number of moles is the number of atoms divided by Avogadro's number. Substituting in, the mass of the ring will be the number of atoms over Avogadro's number times the molar mass. So let's substitute it in now. 3.01 times 10 to the 22 atoms divided by 6.02 times 10 to the 23 atoms per mole times, and we look up in the periodic table, 196.97 grams per mole. Equals 9.85 grams if we get out our calculator. Okay, so in that problem, we did a quick derivation of mass from molecules or atoms, but it's a good idea for us to quickly cover the derivation of that for your notes. So in the previous example, we had N equals M over M times Avogadro's number to get the number of entities from the mass. And we can simply rearrange this to get mass from the number of molecules divided by Avogadro's number times the molar mass. And so this is another tool to have in your quiver. Having said that, really you don't need to do this in one step. If you don't want to, you can always solve this stepwise, where you take the number of entities divided by Avogadro's number to get the number of moles, and then multiply by the molar mass to get the mass. And you can always do this if you wish. So in today's class, we learned how to get the mass from the number of moles, and vice versa, of course. And then we combined our previous work on number of entities to be able to get molecules from mass and mass from molecules. So for the homework, I've chosen a couple of interesting problems from the textbook. Feel free to do more of those if you wish. And please be sure to complete the number of entities worksheet. Thanks for your time.